All right, let's go. Number 10, quantum immortality. A thought experiment, not a proven theory. Quantum mechanics allows for an interpretation called the many worlds interpretation, proposed by physicist Hugh Everett in 1957. In this framework, every quantum event branches into multiple outcomes, each occurring in a different branch of reality. In one branch, a particle decays. In another, it does not. All outcomes exist simultaneously. From this idea, a controversial thought experiment emerged: quantum immortality. The concept suggests that in situations involving life or death quantum outcomes, an observer would only ever experience the branch in which they survive. From their own perspective, death would never be experienced because there would always be some branch where consciousness continues. However, this idea is highly speculative. Most physicists do not consider quantum immortality a testable or accepted consequence of many worlds. It depends on deep assumptions about how consciousness relates to quantum measurement, a question we do not understand. Still, it raises an uncomfortable philosophical question. If reality truly branches endlessly, what does survival mean? Not immortality in the mystical sense, but persistence within probability. Number 9, the Great Filter. In 1950, physicist Enrico Fermi famously asked, "If the universe is so vast and so old, where is everybody?" This is known as the Fermi paradox. The observable universe contains hundreds of billions of galaxies. Statistically, intelligent life should not be rare, yet we observe silence. One possible explanation is the Great Filter, a stage in evolutionary or technological development that is extremely difficult to pass. The filter could be the emergence of life itself, the leap from simple to complex cells, the development of intelligence, or the survival of advanced technological civilizations. If the filter is behind us, we are extraordinarily fortunate. If it lies ahead, then something about advanced civilizations prevents them from surviving long enough to colonize the stars. The Great Filter does not predict doom, but it reminds us that technological progress does not guarantee long-term survival. Number 8, time crystals and exotic states of matter. In 2012, physicist Frank Wilczek proposed the theoretical existence of time crystals, structures that repeat not in space but in time. In 2017, experimental systems resembling time crystals were created in controlled laboratory conditions. Important clarification: time crystals do not violate thermodynamics. They do not produce free energy. They are specific quantum states under highly controlled environments. Speculation about large-scale time crystal civilizations is science fiction, not mainstream physics. However, time crystals demonstrate something profound. Matter can behave in ways that challenge classical intuition. The universe still contains phases and states of matter we barely understand. Number 7, simulation hypothesis. In 2003, philosopher Nick Bostrom proposed a probabilistic argument. At least one of the following is true. Civilizations go extinct before becoming technologically mature. Advanced civilizations do not run ancestor simulations. We are likely living in a simulation. The logic is statistical, not mystical. If advanced civilizations create many simulations of their past, simulated realities would vastly outnumber base reality. We would then statistically be more likely to exist in a simulation. This remains philosophical, not experimentally verified. No current scientific evidence confirms we are simulated, but the hypothesis raises deep questions about the nature of physical constants, information limits in the universe, and the relationship between consciousness and computation. It challenges assumptions without proving them wrong. Number 6, Boltzmann Brains. In statistical mechanics, random fluctuations are possible in sufficiently large systems. In an infinite universe, extremely rare configurations become inevitable given enough time. The unsettling implication: A random fluctuation could theoretically produce a brain complete with false memories more easily than an entire low-entropy universe. This creates a paradox. If the universe were eternal and random, observers should statistically be Boltzmann brains rather than evolved beings. Because we observe a coherent, structured universe, cosmologists use this paradox to constrain models of cosmic inflation and dark energy. Boltzmann brains are not expected in standard cosmology, but they reveal something important. Any cosmological theory that predicts more fake observers than real ones is likely incomplete. Number 5. The Dark Forest Hypothesis. Popularized by author Liu Cixin, the dark forest hypothesis suggests that advanced civilizations remain silent out of strategic caution. In a universe where resources are finite, communication is slow, and intentions are unknowable, the safest strategy might be silence. This idea comes from game theory, not astrophysical observation. There is no evidence that civilizations actively eliminate one another, but the hypothesis reminds us our assumptions about cooperation may not scale to cosmic distances. Number 3. False vacuum decay. Quantum field theory suggests our universe may exist in a metastable vacuum state. If true, a transition to a lower energy state could theoretically occur through quantum tunneling. This would create a bubble expanding at near light speed, altering physical constants inside it. Important clarification. Current calculations suggest vacuum decay, if possible, is extraordinarily unlikely within timescales vastly longer than the age of the universe. There is no evidence it is imminent. But the concept reveals something profound. The laws of physics may not be absolutely fixed. They may be emergent from deeper quantum fields. Number 3. Anthropic Principle and fine-tuning. Physical constants appear finely tuned for complexity. The Anthropic Principle states, we observe these constants because only universes with such values allow observers to exist. This does not imply design, it is a selection effect. Multiverse models attempt to explain fine-tuning statistically, but remain unverified. Speculation about universes almost capable of supporting life moves beyond physics into philosophy. What the Anthropic Principle truly shows is this. Our existence is constrained by the structure of reality in extremely narrow ways. Number 2. The omega point, highly controversial. Physicist Frank Tipler proposed that a collapsing universe might allow infinite computation near its final state, potentially simulating all conscious beings. Modern cosmological data suggests the universe is not closed and is unlikely to collapse. Thus, the omega point scenario is inconsistent with current observations. However, it highlights a deeper question. If computation can simulate consciousness, what ethical implications arise? The omega point remains a speculative cosmological proposal, not accepted physics. Number 1. The Big Rip. In 1998, astronomers discovered that cosmic expansion is accelerating. This acceleration is attributed to dark energy, which constitutes about 68% of the universe. Most data currently supports a cosmological constant, meaning expansion continues indefinitely but not catastrophically. The Big Rip occurs only if dark energy strengthens over time, phantom energy. Current measurements do not strongly support phantom energy. However, cosmic acceleration remains one of the greatest unsolved mysteries in physics. The universe's long-term fate remains uncertain.
Closing reflection. None of these hypotheses are proven apocalypses. Most are speculative. Some are philosophical. All are grounded in real physics discussions. But what they share is this. They expose how little we truly understand about consciousness, cosmology, probability, the deep structure of reality. Science does not eliminate mystery, it refines it. And sometimes, the refined mystery is even more unsettling than superstition ever was.